Hello everyone, myself Ashish Choudhury from IIIT Bangalore, and I will be talking about almost surely terminating asynchronous Byzantine agreement protocols with a constant expected running time. So let us begin with the problem of Byzantine agreement. So we are given a set of n mutually distrusting parties and t of them may be corrupt, and the goal is to design a distributed protocol which allows the parties to agree on a common output. More formally, each party pi has a private bit pi, and we need the following two properties to be achieved by the protocol. The first property is agreement, which demands that at the end of the protocol all the honest parties should have a common output bit, say p. And the second property is the validity requirement, which demands that if all the honest parties started the protocol with the same input bit P, then the final output of the honest party should be the same bit P. So in this work, we studied the BA problem in the asynchronous communication model. So there are inherent challenges while designing any distributed protocol in an asynchronous network model, because in the asynchronous network model, the parties are not synchronized and we do not have any concept of global clock, due to which the channels among the parties have unbounded delay. More specifically, the only guarantee that is given in the asynchronous model is that of eventual message delivery. That means any message which is sent will be eventually delivered. So from the viewpoint of any receiving party, the receiving party cannot make any distinction between a slow but honest sender and a corrupt sender. More specifically, uh, if we consider an asynchronous protocol among n parties, and t of them may be corrupt, then no party can afford to receive communication from all the n parties, as otherwise the uh, wait may turn out to be an endless waiting. So the best a party can do is it can afford to receive communication from at most n minus t parties and proceed to the next step or the next round of the protocol. But in this process, the communication from t potentially honest parties may be ignored. So let us now redefine the problem of BA in the asynchronous setting. So our goal remains the same. We want to achieve the agreement and the validity properties, but now we need an additional property in the asynchronous domain. And this additional property is that of termination, which demands that if all the honest parties participate in the protocol, then eventually they should terminate with some output. So these are the known results in the domain of asynchronous Byzantine agreement. It is well known that asynchronous Byzantine agreement tolerating T Byzantine faults is possible if and only if T is less than n over 3, and this bound holds even if the parties are allowed to use cryptography. Moreover, we have this seminal FLP impossibility result, which states that any deterministic ABA protocol will have non-terminating runs even if one party crashes. So a common approach which has been used in the literature to circumvent the FLP impossibility result is to design randomized ABA protocols, and we have two categories of randomized ABA protocols. The first category is that of 1 minus lambda terminating asynchronous Byzantine agreement protocols, where the guarantee is that the honest parties terminate the protocol except with some non-zero probability lambda. Whereas the second category is that of almost surely terminating ABA protocols, where the guarantee is that asymptotically the honest parties terminate with probability 1. So in this work, our focus is on almost surely terminating ABA protocols, and we are interested specifically in designing protocols which requires a constant expected number of asynchronous rounds in the protocol. So these are the relevant results for almost surely terminating ABA, and we compare our protocol with the existing protocols in 4 parameters, namely the type of networks, the resilience offered, the expected number of asynchronous rounds, and the expected communication complexity. In the expected communication complexity, this F denotes a finite field over which the computations are performed by the parties. So if we consider fully asynchronous setting, then the work of Feldman and Mikali gives a protocol with resilience T less than n over 4, and it has expected constant number of rounds. We improve that protocol by giving a new asynchronous protocol with expected constant number of rounds, and we get a improvement of theta n in communication complexity. Whereas if we consider the resilience of t less than n over 3, which is the optimal resilience, then we give a new protocol which has constant expected number of rounds compared to the protocol of BCP20. But the downside of our protocol is that our protocol is designed in the hybrid network model, whereas the protocol of BCP20 was in the fully asynchronous model. So what exactly is this hybrid network model? So this hybrid network model is not a completely asynchronous model. Here we assume that the first round is a synchronous round followed by a completely asynchronous communication model. So during the first round, we assume that the parties have a global clock. All the messages sent in the protocol will be delivered, and after that, we have the usual asynchronous communication model. So the high-level overview of both our protocols is as follows. Following the seminal result of Feldman and Micali, all the randomized ABA protocols follow that blueprint, and that blueprint reduces the design of ABA protocol to another primitive, namely common coin or CC, which is a common source of randomness for the parties. And the design of this common coin primitive further boils down to the design of another asynchronous primitive, which is called as asynchronous verifiable secret sharing or AVSS. So on a very high level, AVSS allows a designated party called dealer to verifiably secret share a value among n participants in a way that allows for a unique and robust reconstruction of the shared value. And verifiability here ensures that even if the dealer is potentially corrupt, the value is properly shared. So we follow the same blueprint, and we propose two different AVSS protocols to be used in the blueprint of Feldman and Micali to get two different protocols. If we consider the fully asynchronous setting and the resilience of t less than n over 4, then we propose to plug in the most efficient perfectly secure AVSS scheme due to CHP13. And it is well known that t less than n over 4 is the optimal resilience for any perfectly secure AVSS scheme. So by plugging in this AVSS scheme in the blueprint of Feldman and Micali, we improve upon the constant expected round ABA protocol of Feldman and Micali. Whereas if we consider the setting of t less than n over 3, then this result of Patra and Ravi show how to design a perfectly secure AVSS protocol in the hybrid setting and beating the bound of t less than n over 4. So this hybrid setting assumes one synchronous round followed by a completely asynchronous model. So our approach here is that we use this hybrid AVSS protocol, and in the first synchronous round, we generate and we run all the expected number of AVSS instances which are required to generate the expected number of common coins, which will be later used in our asynchronous BA protocol. So that's a rough idea of our hybrid protocol. The full details are available in the paper. So these are the references which are used in the uh, talk. So FM88 refers to the classic work of Feldman and Micali. ADS08 is the almost surely terminating protocol due to Abraham et al. And BCP20 is the improvement of that almost surely terminating protocol due to Bangalore et al. With that, I conclude. Thank you.